So first, what can we actually estimate? We can estimate any technical performance metric that we use to evaluate regression models, with exception of R squared. Likely R squared is not widely used to evaluate models that actually go to production. So we can use root mean squared error, we can use mean absolute error, we can use logarithmic errors, basically any kind of error metric that you have, as long as you can define it on point value, we can estimate it. And what you see here, just an example, we're going to have these estimations, we're going to have confidence bands around our value, and hopefully it works quite well. So what does it actually do? So this algorithm strives to capture, and generally does capture, the full impact of covariate shift on performance. So as you already know, there's two reasons: covariate shift, two reasons why machine learning models can fail or deteriorate: covariate shift and concept drift. This algorithm focuses only on capturing the impact of covariate shift on performance, and also implicitly assumes there is no concept drift. So if your data has very strong concept drift, this algorithm will not work very well, unfortunately. But it still does something, and it is significantly better than doing, for example, data drift, which also can never actually account for concept drift. And also it assumes that there is no covariate shift to previously unseen regions. So imagine that you have a region in space that there was absolutely no data for, or very few data points for. In these regions, the model probably did not learn the pattern correctly. So if there is a strong shift there, the algorithm will not be able to fully take into account the deterioration of performance, fully take into account the impact of covariate shift. But as long as covariate shift is strong, but it's covariate shift to regions we've already seen in the past, this algorithm will do quite fine. So now we know what it does on very high level. Let's talk about what we need to make it work. Basically, we need to provide it with three things. We need to provide it with model predictions, so our actual target predictions. We need to provide with the feature column that we use to develop our models. The same features that you use to develop our model, just pass it here. Very simple. And then it's an algorithm that also learns. It's also a machine learning algorithm. So there is a fitting stage. And for this fitting stage, we need to provide the ground truth or the target. It's the same thing. Depends how you call it. For fitting, and then it's going to learn a specific pattern, and then you'll be able to use it with just model predictions and feature columns. And now, what does it actually output? So familiar visualization, but now let's go slightly more in depth here. So first thing it outputs is actual estimate metric for each kind of a chunk of data or period of data. Let's say it's a week, for which you want to know what is the performance. Of course, performance is something that's potentially very noisy. So we need to aggregate our data to have a reasonable estimate of what is the average performance of the model in a given week, given hour, given 10,000 data points, however you pick that. It also provides automatically determined threshold of acceptable performance based on basically the variability of performance in our test data set or our reference data set, for which we know the performance was acceptable because we verified that. And typically for that data set, for this so-called reference data set, you want to use your test set, because then you know obviously that the performance was satisfactory. And now let's kind of start to establish the intuition behind the algorithm. So what you see here is a very simple model that just takes one feature and tries to predict a continuous target. So we're dealing here with a very simple regression problem. Let's say that we train our linear model. Our linear model is going to learn quite correctly, and it's going to output this pink line over here in the middle. But one interesting thing about this data set is that not only the target is a function of the feature, but also the noise in the prediction or uncertainty of the prediction also changes as our feature one changes. So the higher value of the feature one is, the more spread out the predictions are. There is a word for that that starts with heteroscedasticity that I can never pronounce. That means exactly that the noise in the function is dependent on features themselves. And this is actually true for almost all real-life use cases. And this is the fact that we leverage in our algorithm. And what we do is we basically train another model that takes the error in our prediction for every single data point, and we tries to estimate this error based on inputs, based on our features. So then what we can do is we can estimate the loss based on our features, and that's how we can estimate performance, because if there's regions in our space when the loss is higher, or the expected loss is higher, the uncertainty is higher, we're gonna see lower performance. And just to give you a visualization of how we can actually compute a metric, imagine that your test data or your reference data on the left here are the violet dots. And we also see the expected error or model confidence here in these line plots or contour plots, I think they're called. And we see that most of the data points are in the green region when there is low inherent noise in the data. The model can very easily learn what is the correct pattern and can give our very consistent predictions. And then we see here this kind of mountains on the left and right. And here we see that we don't have a lot of data, but we know that these regions are very hard to predict on. And as we deploy our model, it starts making prediction. There is some kind of covariate shift, so change in our feature distribution. And we see that there is more and more data points in the left and right sides of the feature space. And that means also that the inherent noise in the data is higher there. So our models will make more mistakes and our average error is going to increase in case of regression data. And we can quantify that. And now I'm going to explain exactly how we go about quantifying that. But I hope that the intuition is clear by now. So the algorithm, it basically just takes 3 steps. First is we're going to take our test data, our reference data, and we're going to calculate our loss metric on this reference data. Let's say it's mean squared error. And we're going to calculate this squared error without taking the mean for every single data point separately. Then we're going to simply train a model to estimate this squared error, so this loss metric, using the features of the model and the actual monitored model predictions, because the model, you could treat it in a way as very powerful use case specific way to reduce the feature dimensionality reduction method, basically. So we also take the model predictions because maybe there is some information there that our model would struggle to extract with just the features. We take those two and we actually try to predict the squared error or whatever metric we choose on our reference data and our test data. And then we take this fitted model and we just directly estimate error for every single data point on the analysis data. Then we take the average of that in a chunk in some kind of period, as I already mentioned. And this is something that we can output with reasonable certainty.